So let's take, so I'm starting in front of you, for example, one system. So that's a CoRuMnSi system. Let me make a new directory. So first the student will get this kind of a data. So basically, so if you have expert iScore, you can visualize the data. So the first thing, so if student does not have any prior knowledge on how the structure type is there, so he can actually match this data and search from the database to which it actually matches. So for me, in case of this crystal structure is a cubic structure. So I know about it. So, hello?
Yes.
Okay, so it's working. So can you see this my screen? So it actually matches with cubic. Okay. So useless structures have lattice parameter more than double this size. So if students have Y2O3 tutorials, I have to say. Hello?
Yeah.
So I have attached one more tutorial. So that is a Y2O3 tutorial, FullProf Y2O3 tutorial. So the students can also open that tutorial.
Excuse me?
Yes, yes.
I have a question. Like I asked this before also. Like suppose you're working on an entire new system, and you're not able to get the CIF files or something related to it from the crystallographic database.
Yeah,
So, like,
yeah, okay, that's what I'm saying. So you have expert iScore plus software, right? Okay.
Which one? Which one?
Expert iScore plus. Can you see on my screen? Expert iScore plus. Can you see my screen? Expert iScore plus. Okay, so this is the one. So let me close and open. So open that expert iScore plus software. Okay, so whatever you have the data, XRD data. Suppose if you open, this is my XRD data. So it contains two columns data. So the first one is 2 theta, and the second column is intensity. So this file, what you can do is save it as a .as extension. Okay. So then drag it to the expert iScore plus this software. So you can save the extension format .asc and drag it. So you can visualize the structure. So this is your crystal structure. So as a first thing, what you should go to? You should go to the analysis tab in the expert place and click on the search and match, and there is option called execute search and match. So you will get a new window popped up. So there you select a single phase, okay, and don't give any restrictions, and click search for the possible phases. Okay. So if you do that, you will get a set of here matched patterns. Can you see here? Hello? Hello?
Yes, sir.
We can see.
Oh yes, yes. So there are different systems. So ALNI, CO2, TI, CO2, SI. So like that, you click on the moles and you can see that how many peaks are getting matched. So like that, you can better to identify the type of crystal and type of phases it is matching. Sometimes what happens, you will get more than one phase. So then you need to identify. So some peaks which phase it is matching, some other which phase it is matching. So if you have any doubts, you can mail me. So my mail ID you can ask from them. It's yvenkeswara.1@gmail.com. So if we get any this identifying the phases, I will definitely help you. Okay. So this. In this way, you can get the first idea of what is its lattice parameters and what is the phase you have. So this is a preliminary information you need to know. So that's very important. Sometimes you need to identify from the literature, sometimes using this one. So basically we needed to identify what type of it's a cubic. If it's a cubic face center or primitive, then tetragonal. So first we need to identify. This is the first information. So then what you should have your data file. So I have created a new file. So I'm starting from the beginning. So there are different ways people usually organize the data. So some people organize starting angle, step size, final angle, and then intensity in the next column. So now I usually arrange it in a XY format. The first X, the column is correspond to theta, and second column corresponds to intensity. So this file we need it. So I had told you to download this FullProf Y203 tutorial, so which is very nice tutorials. They have given with graphical screenshots also. So you first open your FullProf tab. Okay, by clicking this one, and you select the working directory, and so you go to the where you are doing this folder. So mine is on desktop. I kept this refined folder. You just copy this one path and paste it in working directory. So make sure that your working directory should not contain any spaces. That's very important. So for that you can change it to your D drive, other D drive. So then what you need to do is you open this win plotter. You click on this win plotter. So in win plotter you open the data file. So mine is XY column. So just click on that one. So it will open in the working directory. So we have plots. So here now first step is we need to generate PCF file. Okay. So I prefer to create the PCF file for XRD systems. For neutron systems, better to copy from their some default PCF files. So if possible, tomorrow I will discuss the neutron diffraction refinement. So today I will focus only on XRD refinements. So as a first thing in this win plotter, we need to select the peaks. So okay, so it has peaks. So select something like 6 to 7. Is different. It depends upon different crystals. So you need to select sometimes 20 peaks also. So mine is a very simple system. So I'm selecting the. So there is called automatic peak search. You can visualize it here. Okay, you click on that auto peak, and remember this radiation is copper K alpha radiation. So you search for select for the second option. Okay, and you try for selection. So how many? So it is generating too many peaks. This is not good. So you repeat the process again. So with different parameters. Okay. So here for my case, for second option, it is generated 4. You can also try with the different options like okay. And if any missing peak is there, so you can add it manually. So like say add peaks. So automatic add remove background peaks. Okay. So you select manually some of the peaks if some peaks are missing. Okay. So then save these peaks for the first option. So this is first there are different okay. So my system I know that is by preliminary idea it's a cubic. So I'm selecting some okay minimum 160, and I also select for zero shift if is there any zero shift, and give some impurity peaks something 2 or 3 whatever means some in the selector list. And try to run it. So here is my lattice parameters that I am expecting 5.77. So that we got it from here one. You can see here in the expert I-score plus it's coming around 5.78. Okay, that's close to this one which I am getting. So 5.7769. So So we got so in your different if you have different space systems, you may get end up with different possibilities. So you need to select which one matches. So it creates different PCR files. Here in my case is only one such is found. So it will create one. For sometimes it will create more than one. So you need to identify which one actually better suits the refinement for the selected peaks. So let me click OK. So then you can see here in the reference folder there are different files are created. Okay. So is everybody is clear with this this information? These steps so far I have done. Hello. Hello.
Yes, sir.
Up to here everybody is clear. So you'll get a set of files in the refinement folder. So we are interested in .pcr file. Okay, let me open that one. So let me close this for the time being. So you click on EFP symbol is there, that stands for the Rietveld program file. So, it will open. So there is a PCR file. That PCR file, you just open that PCR file with Notepad or some Notepad++. I will open directly. Okay, so here you make sure that the radiation is copper radiation. So lambda 1 is 1.54 and lambda 2 is 1.5444 should be there. Okay, this is approximately. This you should make sure, and ratio should be 0.5. This K alpha 1 to K alpha 2, the intensity ratio is 0.5. So this you should make sure that. And here you can see that space group. So you change the space group also. Mine is a face center cubic system. You change it AF minus 43. So in the first step, you change the space group what we are expecting for your crystal structure, and then save this before opening first time. Then you open it. You open the data file. So you can see here. This method we didn't provide any structural information what we have given. So if you click on edit PCR file, you can see here in the refinement section, if you click, so the items tab is disabled because we have not provided any crystal information where the CO is sitting at which place and RE is sitting at which place. We have not provided any atomic information. What we have is just a profile information. So this profile information tells the what type of crystal it is. It's a ABC and alpha, beta, gamma. So this tells the what type of structure we have. It's a cubic or hexagonal, what we have. Then full width of maximum. So these are instrument specific. If you know, we can directly give. Otherwise, what we have to do is we have to play with this. So this will give this full width of maximum of these peaks, the reflections. So then some eta 0 is there. Anyway, so we have to play with ABC values. Okay. So because ABC tells give ABC this. Cell parameters gives this D values, set of D values. So that set of D values tells that where we get the satellite peaks, because it's a 2D sin theta equal to n lambda. So first we need to fix this peak positions. So there should be no mismatch in the observed peak position and your estimated peak position. So first step you should, so this is very important, you should follow in a sequence manner. You should play with the ABC and alpha, beta, gamma. So alpha, beta, gamma is fixed for cubic. I'm playing with ABC values. Okay, and you save and you just practice it until you get lower chi-square values. Okay, and you can also zoom it and see that. So here right now is I'm peak shape, full width of maximum is not matched, so that I will play with that next step. And during that time you keep ABC values same, and So this eta 0 is a shape parameters. How the shape is changes. It's a broadening. So if you increase eta 0 value, the peak broadening happens. So you play with changing manually and see how it actually changes. And I can see here clearly in the calculated. So K alpha 1 reflection and K alpha 2 reflection, they are clearly resolved. Whereas in my experimental data, the red plots points, it's not visible. So this tells that this full width of maximum actually it's a broaden. So that means this K alpha 1 and K alpha 2 they are actually the peaks. The resolution is not there. So when the resolution is not there, this is more broadening. So that in that case, you have to play this UVW values. Okay. So this also you play manually because sometimes it diverges. So you change manually this UVW values. Okay. So these are the routine steps. If you follow it, anyway, so you will get best refinement and your chi-square gets reduces. Okay, and you make sure check with all the remaining peaks. So do it these two steps until you get a best best fit. This is called label fit. Okay, I'm leaving this as an exercise. Okay, you can practice it. So until you get chi-square as least as possible. Okay, so this is the first step, and sometimes this background intensity. That's a background. So that background people do with different parameters. So here, if you see this background, so we have selected background points. So you can also refine all of them. Okay, so. So somewhat fine. So this is called label fit. So the first step one has to achieve this one. If the student is unable to achieve this step, so he will has to face a lot of trouble in the next structural refinement. So.
Excuse me.
Yes.
Is there any limitation for the values of UVW as one of the value was negative when you were fitting them? So is there any kind of limitation that these should have positive value or negative value or any value is allowed?
This actually related to your XRD mission. So it actually people don't give. So we have to play with this UVW values. Okay. This UVW actually tells whether we can see this splitting of the K alpha 1 and K alpha 2. Okay. So I have seen for different structures, these are different. Okay.
We can have negative value we can put? Negative?
Yeah, you can put negative.
Okay.
Yes. So this tells only whether the resolution is there or not. Okay. Now you see that K alpha 1, K alpha 2, the resolution is merged it. So this we need to play. Sometimes what happens, we can actually do one thing. You reduce cycles of refinement to 1, and okay, and you take UVW values. Okay. Sometimes diverges. Make sure you copy those previous values. Copy it by this one. Okay. And do one time run once, okay, and check whether you are getting improvement, and then run once. Okay, now you see it's gone bad. Okay, it's gone bad. That's why this is better to change manually, not by automatic method. So you see that they actually pick up large numbers. So I'm pasting back the old values. And so one can also do not in the background, in the instrument, zero shift, whether there is a shift in the from the theta value. So the 2 theta is a plus or minus correction is there or not. You can also try with the zero shift. Okay.
Sir, hello.
Yes.
For data, they generally ask for instrument while when we analyze this data and all.
When you analyze, basically this UV parameters is related to the instrument, but sometimes they also changes for this our XRD pattern. So it is our duty to first whether we will get the this label fit properly or not. So this is the first important step. So there you only play with the cell parameters, that is ABC and alpha, beta, gamma, and UVW values, whether you see that really there is a splitting of the K alpha 1 and K alpha 2 peaks, and you play with them so and get the proper refinement. So once we are happy with this, we are ready to move with the second option. So that is called Rietveld Refinement. Sometimes what people will have is they don't have any information how the positions are there. So if they go to hexagonal structures, okay, that thing I am going to do it in the Y203 tutorial. So this I'm starting with this known systems where the positions are fixed. Okay, so first one has to complete this procedure. Once the student is happy with this label fit, so you exit it. Okay.
Excuse me.
Yes.
What is this blue curve is representing? Red and black are experimental and the fitted one. What this blue one is representing?
This blue is the difference. Blue is the difference between red data and black. Black is the calculated one. So the difference it actually tells.
Okay, so for the best fitting, should we have this kind of horizontal, means the difference should be 0?
Yeah, difference should be 0. Yes. We should have the flat this blue data. Okay. Sometimes. Yes.
Sorry. Any limitation for this chi-square value?
Chi-square is better. Limitation is anything less than 5 will be fine. Less than 5. No, sometimes actually the chi-square, we should not look at the chi-square. Basically what it happens if you increase this background, okay, background is more like, say here it's a 2000 count, okay, if we have something like 6000 count, then chi-square comes very less value because chi-square contains the background data. So we should not trust your chi-square value, but what we should trust is the another one. So let me show you that one. Okay, so there is a bragg factor, bragg contribution. So here, this one, bragg factor is there, right? So we should consider RF factor and bragg factor. Okay, these are independent of the amount of your background in the XRD pattern. So one should actually consider this bragg R factor and RF factor. These are irrelevant. What I have noticed is if you change the background, suppose manually you add some quantity to all of the data, okay, something 1000 counts. So basically there will be no change in your XRD. But the chi-square is seems to be going down, whereas this RF factor and bragg factor are not changing. So basically one should focus on these factors also. This should be very less. So in my case, it's 1.3, 1.4. Okay. So this is a label fit. One has to focus on this because here we are focused on the positions of the reflections. The positions of the reflections is given by the equation 2d sin theta equal to n lambda. That d is actually specific to the type of crystal. So that is crystal means it's ABC and alpha, beta, gamma values only. So it is not related to so here we are not focused on the what you call the peak intensity value. We are not interested in is there any difference between the peak intensity. What we are interested in the peak positions. Remember that 2d sin theta equal to n lambda gives the reflection positions where your reflections are happening at what position. But we are not focused on the structure factor, because the structure factor gives the intensity. As we see in this slide here you can see that so the intensity is proportional to structure factor square. So we are not interested right now on this quantity. That quantity we are focused on. So how much is intensity between calculated and experimental, that we are focused. We are going to do it in next step. So and this, at that time, you people don't try to refine the cell parameters, because cell parameter only gives the position, relative positions of the peaks. Okay. So let's go to the next step, that is called refinement. So okay, so people can also get the electron density from this one also, if the people are interested. So for that you can follow this tutorial. So okay, there is called FOU equal to 4 options will be there. If you open the PCR file, okay, here FOU is equal to 4 is there. You change it to 0 to 4, then you will get this Fourier transform maps. Okay, that you can visualize using Fourier. So for that you have to run only once. You no need to refine any of the things. So here there is a Fourier Fourier program is there. It really what it does is that this is it does the Fourier transform of your XRD refinement details into real space. So then you will get the definitely the electron intensity map you will get in the cell. So let's calculate this one. So it gives this. This is a real space. It's a cubic structure, so it's a and B. So another direction, your C direction. So here you can see that this refinement, it gives this this counters map. So you can actually play with the different patterns are there, the different visualizations are there. So let's stick to this one. So there are thick counters are there at the origin location. Another is off 0 0. So mine is a crystal. This is a useless structure. So these are the expected locations that are displayed. Okay. So if people don't have any idea, so they can also estimate where the atoms are there. And okay, sometimes if relatively less intensity atoms are there, this density will be less. So you can sweep along z direction by pressing this one, and how the intensity actually changes. Okay, and you can play and identify the how many atoms are there, and you can get these different possibilities. So this leaves me, there are 4 in useless structure. Okay, let me write here. This is quaternary usular array. So I have 4 locations. So let's it has one location is 0 0 0 FCC, and second one is 0.5 FCC, and 2 more locations are there. There's 0.25 0.25 FCC, and the last one is 0.75 FCC. So we have 4 different sites are there, and FCC means we have to add FCC means you have to add 4 other locations. That's fundamental to the FCC term. So you have 0, 0, 0, and 0.5, 0, 0. Sorry, 5. 0.5, 0, 0.5, and another location 0, 0.5, 0.5. So you have to add this to this basis vector. So you will have, there are 16 locations if you count in this one. There are 16 locations. So now I have 3 possibilities. So the student has to do for different possibilities. So suppose let me treat one atom fixed at one location. Say silicon, I'm taking at 000 FCC location. Say let me keep this one silicon. So what left? It actually left is like now three locations are there. So which gives me a lot of possibilities. So one can actually keep here one possibility. Like say it's CO. Okay, and if we keep CO here. What you will get here, Mn. Another one option is called Ru. So this is one set of structure. So you will have different another one. So if you keep also one the other student, so other possibilities like so here extra student can keep Mn and you can keep CO here and like this one. So you will get something three possibilities are there, and it is student duty to identify different possibilities and do the refinement for all different types. So do you got it? Hello?
Yes.
Yes, sir. Yes, sir.
So you should identify what are the different possibilities are there, and you should do the refinement for all the possibilities and select the best one. Okay, so that is our task in the refinement process. So in the refinement process, the student does not get immediately the what is the best suited refinement. So he has to refer the different possibilities. So he has to look for the whether CO seats are this location, whether Mn seats are this location. There is one more is RE seats are this location. So he has to write down in a notebook and find out the different possibilities. So that is next step. So let me create this refinement file, one file. Okay, so you can open. So that leaves these atomic positions, and the student has to make different possibilities. So let me open this one again. So this one, your piece label plate information. Now we have to provide the okay, you can run once matter. So you go to the edit PCR file. So what we are going to do is change this title to someone. Okay, you say that configuration 1. So this one configuration. What we need to do is now is the refinement. So sometimes we can actually skip this. Okay. Okay. Sometimes people can exclude this range, refinement range. It's not matter right now. So let's go to the phases. In the phases, you change it to, this is very important, structural model Rietveld method. Okay, so that means now once you select this one, this atoms keyword will be enabled. Earlier it was disabled. Now contribution to patterns, this you change it to this one, you generate from the space group symbol. Okay, don't read the earlier we had HKL values when we do refinement, so don't do that. Read from the world value, select the automatically generate from the space group, and make sure that X-ray is selected. And is symmetry, that earlier we have given the space group. If you want to change it space group also, there you can change it. Okay, so this is task. Once you have done, now you can click on the refinement section. Now you can notice that atoms tab is highlighted. Okay, we got. So in the atom tabs, now if you know the space group, so what you do, you search for the Y-cup positions. for your space group. So you get search in the Google, okay, and so identify the space group. So it's for me is F minus 4 3 means 216. So click on the space group and enter it. Okay, so if you enter it, now you are left with different possibilities. That's what earlier I have told in the PowerPoint. So there are 4 different locations are there. Okay, so there are some are fixed locations are there, like 0 0, off, 1 by 4, 1 by 4, 1 by 4, 3 by 4, 3 by 4, and some general locations also there. So at different locations, site symmetries also are there. So we need to have different possibilities. That's what I'm saying. So in my system, so there are 4 items are there: CO, RU, MN, and SI. So I'm keeping, say, first one is first configuration I'm taking. So this one, okay. So keep silicon at fixed at on 0 0 location. So keep 4 there. So for label is silicon, type is silicon, and your X location is 0 0 0, and P is your thermal factor. So that due to the temperature, the atoms are always vibrating. You give some number, should be always positive. It does not give negative. Okay. So thermal factor, the B should be always positive, and give occupancy is 1. Okay, and I will tell you how to calculate the occupancies. And so second location CO, and CO is equal 0.5, like what we assumed earlier. And this MN 0.25, 0.25, 0.25, 0.5, 1, and RU 0.75, 0.75, 0.75, 0.5, 1. So there is a term called isotropic, means in XYZ directions the atom is vibrating isotropically. And sometimes you may need to refine with anisotropic, then this P will be disabled and you will get a different so directions. You will be having different terms. Okay. Okay, so right now I'm assuming that isotropic. What we are focused now is whether this structure will match or not. So that is our task. Okay, you click OK, and make sure that if earlier ticks are there, you disable it. Okay, and background also, if you have selected earlier, you click fix all. Okay, and for the time being, you keep 1, and you this one profile matching mode earlier we have selected. You keep local divergence, because if any divergence is taking too much time, it will stop it. So you click OK, and you save this as a refinement 1. So you can say configuration 1. So and save it. Okay. So do you got my point? Now what we have done is we have changed this label fit PCR file to structural refinement, and let's run that one. So you open that one, the second one here, configuration 1, and see how whether it will match or not. So that is our task. Okay, you run it. So and so here, okay, the scale parameter we have to first do the refinement. Go to the refinement and go to the profile. You select the scale parameter and don't select any other thing. And okay, you can keep number of cycles 10 automated, and save and run. Okay, so as you can see here, something is not matched. So here now we are not interested in the peak positions, but what we are interested in the intensities of the peaks, calculated and observed. As you can see clearly, this peak that is called this is called 111 peak. The 111 peak intensity is not matched at all. And okay, so this one anyway, it's a small. First we need to do is refine in such a way that maximum peak intensity matches. So then you identify what is the mismatched intensity peaks. So here in this case, it clearly tells that first peak, that is called 111, reflection did not match. So notice that. So if you click on this one, you will get that reflection 111, and you do the little bit analysis of the XRD. So the here now you should focus on why it is not matching 111. So how can you write 111 peak structure factor? So structure factor. So you also please practice on your notes. Duplicate no slide. So what we have kept it here like this one. Hello. Hello.
Yes, sir. Yes.
So this is your information, structural information, what you have provided. So now your student duty is to identify why it is not matching. So for that, the student has to focus on the structure factor. So structure factor here, write down the structure factor for your first configuration what you have chosen. So in my case, it is like yes, it's hello, yes.
Kindly proceed, sir. No issue.
Yes.
Yes.
Hello?
Kindly proceed. No issue.
No, I'm writing. So you see, your student's duty is to find out this. What is the structure factor for 111? Okay, and identify why it is happening. So if you write it here, so you will get term. So so silicon. So that is on 0 location, and place then cobalt at F CO E for you'll get pi I. Plus K. So like that you will get term. So basically then you can identify that it is because of some difference in the peak position, this structure factor because between CO and SI or MN SI, and you identify different possibilities. So then we will identify, okay, this, you will get like this one, and you write it for all the structure factor completely. Then we can identify that, okay, there is a disorder. We can identify that CO and SI disorder will be there on peak. This one check whether this peak slightly change in this configuration one, but with a different disorder. So you just open it one and you change the PCR file. Okay, go to the refinement section and go to the atom. So now what you do is do the
Thank you for watching. Please subscribe, like, and share.